All right. So, hi everyone. So today we're very happy to have Shreya visiting us from Stanford. She'll be talking about estimating time in quantum chaotic systems and black holes. Shreya got her PhD in 2022 at MIT, working with Hong Liu. Now she's currently a postdoc at Stanford University. She'll be here tomorrow as well until the evening. And she's sitting in 228. 228.
Yeah.
Yes, if you want to talk. All right, please.
Okay, great. Thanks a lot for the invitation to speak. It's a pleasure to be here. It's the first time I'm in Purdue. So I'm going to be talking about some work in progress with Haifeng Tang, who is a graduate student at Stanford, and Jinzhao Wang, who is a postdoc there. And the subject of my talk is estimating time in quantum chaotic systems and black holes. So I'll explain what this means. So let me start with some background and motivations. And in particular, let me start with some background just from general quantum many-body systems. Okay, so in general, if we have a system with chaotic interactions, we expect that any initial state equilibrates at late times. So for example, if we have this kind of very specialized initial state for a gas in a box where all the molecules are on the left half for some reason, then we expect that at late times, the system will evolve rapidly and then reach some kind of steady state where things don't change very much at late times. Okay, so in particular, we're interested in quantum mechanics, and we're interested in some quantum many-body system, which evolves some initial state psi 0 to a time-evolved state under h. And under such evolution, we might imagine that if we look at an observable, like the density of particles at some point in the left half of the box, in this case, then roughly it just relaxes somewhat smoothly and then goes to some value which is kind of constant at late times. Okay, so there would be some fluctuations on top of this, but not very significant ones. And in contrast, if we consider a very specialized kind of system, like an integrable system, where, say, maybe there are no interactions or there are very fine-tuned kinds of interactions, then the evolution might take a very different form where initially the density might go down, but then it might show some very irregular behavior, like it might go up again and then decrease, and then particles might all oscillate together or something strange like that might happen. But generically, we expect the situation on this left half. And in particular, if we're at late times in this kind of scenario, then we expect that, just from this picture, from this particular observable, and for most observables, we shouldn't be able to do very much to distinguish different times in this regime from each other. Okay. So the goal of this talk will be to make this idea more precise. So in particular, we try to precisely quantify our ability to estimate the time t by making some measurements on the time-evolved state psi of t. And we'll ask questions like whether, as this picture suggests, our ability to estimate times becomes negligible at late times if we have a chaotic system. But perhaps it's better in the case where we have an integrable system where it seems like things might still be evolving non-trivially at late times. Okay. So this is what we'll try to address. This question turns out also to be relevant for describing the physics of black holes. Okay. So we can think of black holes as an example of highly chaotic thermalizing systems. And in particular, we might imagine that we start with a star, which is in a pure state psi 0, which collapses to form a black hole. And subsequently, we know that the black hole emits some thermal radiation. And over the years, say the last 40 years or so, a lot of evidence has been gathered that black holes can be seen as examples of highly chaotic quantum many-body systems. So in particular, if we think about this process where a star is collapsing to form a black hole, this process can be seen as the process of approach to equilibrium in the figure that I had on the previous slide, where things were in the process of decaying in the system. And then at late times, we know that the black hole emits some thermal radiation. And at each time during this process, for each size of the black hole and radiation, we can think of the combined state as some kind of equilibrated state, like in the part of my plot in the chaotic system where things had kind of settled down and were not changing very much with time. Okay, so there is a gradual transfer of degrees of freedom from the black hole to the radiation, but that happens on very slow time scales. And I want to think about a case where maybe we can think of this essentially as a static situation for a particular size of the black hole and radiation. Okay. So in this context, we can again ask if during this process of approach to equilibrium, somehow as the system is relaxing, does our ability to estimate time get worse as time evolves? And in this context, there is also a natural question of whether we expect that we won't have access to the degrees of freedom of the black hole. But if we only have access to the degrees of freedom of the radiation in this case, then how does our ability to estimate time change? Okay, yeah.
So BR is pure? State of BR?
Yeah, right. So if the initial state was pure, then we are assuming that this is like an equilibrated pure state. Okay, good. So we might expect that in what I've said, it seems, so I've discussed what we expect from our intuition about thermalization, but that is essentially based on the fact that at late times, I'm assuming that my state looks something like e to the minus beta h over z or some other equilibrium state. And such states don't evolve at all with time. Their commutator with the Hamiltonian is just 0. But we know that it's not quite true that the state cannot actually become equal to e to the minus beta h over z. We know that, if you're writing the evolution of some pure state in the energy eigenbasis, it has some expression like this. The commutator of this with the Hamiltonian could never actually become 0. So it does actually continue to evolve with time. And so we might expect that this question of estimating time will reveal some kind of tension between thermalization and unitarity. Okay, and in the context of the evaporating black hole setup that I described on the previous slide, there's another kind of difference between e to the minus beta h and the actual equilibrated pure state psi of t, which plays an important role, which is that e to the minus beta h essentially contains no information in some sense, which we can make precise by studying things like the entropy. And psi of t does contain information in a highly scrambled form. Okay, so in particular, if we look at the entanglement entropy of some subsystem, then unitarity puts constraints on how that has to behave in this time evolved state psi of t. So the entanglement entropy of any subsystem has to be equal to that of its complement. And that is a constraint which has to be obeyed in this actual time evolved state, but is violated by e to the minus beta h. So we might ask if in our present question about estimating time, does unitarity also put some constraints on this question? Okay. Great. So in this talk, when we talk about black holes, we'll be treating general chaotic systems as models for black holes. And let me explain sort of an example of how we apply this reasoning for quantities like the entanglement entropy. Okay, so in that case, we consider that we have a pure state, which is equilibrated and divided into two parts, B and R. And from unitarity, as I mentioned, we have the constraint that we have to have SB equal to SR at all times in the evaporation process, where S is the entanglement entropy of the reduced density matrix of rho B or rho R. Okay. And in contrast with this expectation, when Hawking did a calculation of these quantities in semi-classical gravity, he predicted that they follow, that the number of degrees of freedom in the black hole follows this blue curve. Okay, and in particular, that's an upper bound on the entanglement entropy of the black hole. And he seemed to be finding that the entanglement entropy of the radiation follows this red curve. Okay, so in particular, at times beyond this halfway crossing point, called the page time, the entanglement entropy of the radiation becomes larger than the largest possible entanglement entropy of the black hole. Okay, so that gives us a very sharp contradiction with unitarity. But it's expected that black holes should not be too different from ordinary chaotic quantum many-body systems and should still obey the usual rules of quantum mechanics. And if we assume this and make the assumption that the dynamics of a black hole are both chaotic and unitary, then a very natural model for the late time combined state of the black hole and the radiation is just that it's a random pure state. Okay, so in particular, we can model the combined Hilbert space of the black hole and radiation as some finite dimensional Hilbert space. And Page considered just a case where you have some finite dimensional Hilbert space divided into two parts, A and A bar. And consider the entanglement entropy and consider random pure states with a uniform measure in the system and the entanglement entropy of the subsystem A. And he found that it's always given by the minimum of the log of dimension of A and the log of dimension of A bar. Okay, and by applying this result to the case of the evaporating black hole, by taking A to be either the black hole or its radiation, we obtain the expectation that both should follow this solid line, which is the minimum of these two curves. Okay, and this prediction, based on just general properties of chaotic quantum many-body systems, was recently confirmed more explicitly using a gravity calculation, which involved including certain new elements into Hawking's semi-classical gravity calculation, known as islands and replica wormholes. So this whole process of making predictions based on general chaotic quantum many-body systems also ended up teaching us new things about just features of gravity. Okay. So in this talk, our goal will be to make a similar level of prediction about what happens during the evaporation process by using general properties of evaporating black holes, but for this new question of estimating time. Okay. Okay, so let me explain more precisely what the setup is and what I mean by the question of estimating time, etc. So we imagine that we are given some, say, large number of copies of the time-evolved quantum many-body state, psi of t plus delta t, where it's evolved from some initial state psi 0 under some Hamiltonian. And the things we know are that we know what psi 0 is, and we know what the Hamiltonian h is. And say we also know that the time is close to some time t, but we don't, so we know that the time is t plus delta t, but we don't know what delta t is. Okay, and we want to make measurements on this time evolved state t plus delta t in order to deduce what delta t is. Okay, and we can also consider the case where we consider the reduced density matrix on some subsystem of the whole system. And again, we might then want to make measurements that are restricted to the subsystem to try to figure out what t is. Okay. Yeah, and in the context of the black hole, let me just rephrase this question. So in this case, we imagine that we're given many copies, but now we only have access to the radiation. And again, maybe we know what the initial state of the star was and what the dynamics of the black hole are. And we want to now use, say, n copies of the radiation to try to estimate what delta t is. Okay, so for this, just to introduce the relevant, yeah.
Sorry. So, but there is some sort of you're probably taking some scaling regime, right? So the entropy is, yeah. How does T compare with entropy?
Of the black hole or radiation?
Yeah, the system you're trying to model is a many-body quantum system. Let's say it's n qubits.
Yeah.
Right? And you're going to take n to be large.
Yeah.
But you're taking T, how does T scale?
Yeah, I want to consider some intermediate time regime during the thermalization process.
So T is not
could scale with
significantly less than 2 to the power of minus n. So it's not enough to resolve the individual gaps, right?
Oh, you mean delta T has to be smaller than that?
No, the T. So.
Oh yeah, T is not exponentially large.
Yeah, T is okay.
Yeah.
So poly in that.
Yeah. Yeah, that's the regime we'll be interested in. Great. Any other questions? Okay. So how do we quantify something like our ability to estimate time? Before doing that, we can just have a general discussion of how to estimate any parameter. So suppose I have some one parameter family of states, rho of x, which are labeled by some continuous parameter x. And in our case, we'll take it to be t, but the next few slides can just be seen as a general review of how to estimate the parameter x given any such family. So yeah, so the setup is that we are experimentalists and we're given some capital N copies of the state at some particular value of this parameter x, which is, say is x0. And then we want to figure out what x0 is by making measurements on rho x0. So in particular, say we have some spin 1/2 chain, something very concrete we could imagine is just choosing to measure the Pauli Z operator on all sides of the system. So for the first copy, we measure Z1 through ZL and we get some strings of zeros and ones. And then we repeat this on each copy and get some n strings of zeros and ones by performing such measurements. And then based on these measurement outcomes, we want to come up with some estimator function, xest, which takes these measurement outcomes as input and outputs a guess for the parameter x. Again, we want to then see how close our guess can be to the actual value of the parameter.
So yeah. You're formulating like a parameter estimation problem, right?
Yeah.
Sorry to interrupt. Hi, everyone. Was this an individual study? Was this room reserved for a certain time?
Yeah, this was reserved for a seminar.
Okay, perfect. Until what time?
3:30 until 4:30.
Okay, perfect. In unit time, it's just an individual study, so Thank you.
You were asking a question about
Yeah.
parameter estimation.
Yeah, so the way you're formulating it sounds like parameter estimation, right? This
Yeah.
sort of-
Yeah, it's exactly that. Yeah. Now, but for us, we take the parameter to be time. Yeah, so right, so we come up with some estimator function, and we want to see how close it can be to x0.
So what's one of the choice of for this policy arbitrary or so?
I'm just giving an example here. Eventually it won't, well, sometimes it will be, but for most of our talk, the measurement basis will not be the policy.
So essentially one can choose whatever measure.
Yeah.
Whatever, so
Yeah, yeah,
because one of the result will depend on the choice of the measurement.
yeah.
Right.
Yeah, it will depend, the optimal measurement, so, right, so you could make many different choices. There will be some optimal measurement basis, it'll depend on the specific state as well.
And how are we going to judge which one is the optimal, which one is the best choice?
So this is why, let me do a couple of more slides and then I'll be able to answer your question in a more precise way.
But you wanna do it in a way that's independent of initial state. Is that right? You wanna,
No, not necessarily.
so you are.
In fact, like I mentioned, this local parameter estimation task, that the time is close to t plus, like the time is t plus delta t for some small delta t. The place where that comes in, I guess in partly in answer to your question, is just that the measurement basis will depend on rho of t, the optimal one. So yeah, like if you just take the one corresponding to rho 0, you won't be able to do as good of a job. Okay, but so far, let's just say we pick some particular measurement basis, which is most convenient for us in our lab. Okay, so then our question is how well can, and we have not only a choice of the measurement basis, but also a choice of which precise function to choose here. But say there was some way to figure out the best possible function, xs, then how close can that get to measuring the parameter x0? Okay, so, and the answer to this question is relevant because if no estimator is able to do a good job, then this tells us the state is not changing very much with respect to our parameter, at least in this particular measurement basis. Yeah, so we can give a precise way of quantifying how good this estimator is by, say, considering all possible outcomes, psi1 through psi-n, with the corresponding probabilities, and then looking at the average value of this quantity, which measures how far x(est) is from the actual value of x0. Then we'll consider the average in the probability distribution corresponding to the actual value of the parameter. Okay, so.
Why separado?
Say again?
Why separado? The probability shouldn't be for all cases.
Because right, because I had n draws from this distribution.
Sorry, each side is a set of all sides.
Yeah. So each psi is a set of all zeros and ones.
Okay.
So I had some probability corresponding to that, but then I had n independent trials of this thing. Yeah. Okay. So this is the quantity we want to study. Yeah, and these p's are just given by the probability of measuring this outcome in the given state. And now this can be seen as a purely classical question once I have this expression, because I just have some classical probability distribution which has some parameter x0 in it, and I want to infer that parameter by drawing samples from the distribution.
The samples are IID, I guess that's the question that was asked.
Yes, they're IID, yeah. Okay, and as you can imagine, this is not really a question about quantum mechanics anymore. This is a question which comes up all the time in very real situations where you might want to estimate some parameter by making measurements in some situation. And this was addressed a long time ago, like in the 1920s, in the statistics literature by Fisher. And it turns out that for any over all possible choices of this estimator function, this quantity has a lower bound, which is expressed just in terms of intrinsic properties of the probability distribution. Okay. So this bound takes this form where this object is greater than or equal to 1 over n, where this capital N was the number of samples that you drew, times something called the Fisher information, which is this combination of the probabilities. So as you might imagine, this involves a derivative of the distribution with respect to x, because if the distribution is changing more with x, then you have a better chance of estimating it. If it's not changing at all, then there's nothing you can do to estimate what x is. And yeah, so this is Yeah, so this is telling us how quickly, as we increase n, our variance is getting smaller in our measurement. And not only is this a lower bound, but it's also saturated in the limit of large n by some particular very explicit estimator function known as the maximum likelihood estimation. Okay. So this Fisher information gives us a pretty good way of quantifying how well we can estimate the parameter by making measurements. Okay. And okay, so as we already kind of anticipated, for a particular choice of measurement basis, we can consider the classical Fisher information associated with that. But if we are given some quantum state, then we can also ask what is the maximum value of this classical Fisher information over all choices of the measurement basis. And this is given by the quantum Fisher information. And it's possible to do the minimization very explicitly in the previous formula, the maximization very explicitly in the previous formula of the classical Fisher information. And you get an expression like this, which you don't need to pay too much attention to the details, but again, it involves a derivative of the density matrix with respect to x. And it involves the eigenvalues of the density matrix and its eigenvectors. Okay. So because now it turns out that the choice of the measurement basis, which is optimal. Yeah.
So psi and psi j's are the eigensets of the, I see.
Of rho of x.
So basically we wrote it as a classical problem. You're writing it as a classical problem in the eigenbasis of the density matrix.
It's the optimal basis is actually not the eigenbasis of the density matrix. It's something else, which is like related to this object. Yeah, so
Yeah, okay, so the time derivative of rho need not commute with rho, sure.
Yeah, if I had just chosen a measure in the eigenbasis of the density matrix, then I would just have got the classical Fisher information associated with the eigenvalues. But this is not that, and it also involves the eigenvectors in a non-trivial way, which is very important for the rest of the discussion. Okay, but there is an explicit measurement basis, which I can discuss more later if you want. But yeah.
It's the result of a supreme number, right, over all measurements.
Yeah. Yeah. Okay, so good. So the right now, because our choice of the measurement basis depends on rho of x, this only tells us how well we can do locally at estimating x, because of course you need to know which basis to measure in to make this measurement. And that's why I had phrased the question earlier in terms of like knowing that your time was close to t and then wanting to figure out what delta t is. Okay. And this is also another way of getting some intuition for this quantity is that it's related to some distance between the state at x and the state at x plus dx divided by dx. So it can be seen as some kind of intrinsic velocity associated with changes in the state in the case where we take x to be t. Okay. Good. So the plan for the rest of the talk will be to first discuss general properties of this expression and what constraints we get on it from unitarity. And then I'll discuss the results for chaotic and integrable spin chain models, as well as for random pure states. So those will be the main results. And then we'll discuss the consequences of those results for evaporating black holes. And we try to physically understand them in terms of what they're telling us about the structure of the state. And finally, I'll change gears a bit in the last part where I won't consider the quantum Fisher information, but instead the classical Fisher information associated with simple measurements and see how that behaves differently. Yeah.
Is it correct to say that what you're studying is the Fisher information between well, it's a relative entropy between rho and rho plus delta rho, where delta rho is I commutator Hamiltonian rho.
Yes. Yeah, but sometimes when I take the reduced density matrix, then I take the partial trace outside of the commutator.
Ah, okay, that's right.
Which
that's
is
right.
very,
That's important.
yeah, that makes an important difference. Okay. Yeah. So let me first discuss general properties. So from the intuition that I mentioned on the first slide, that the state is relaxing to a steady state, we might expect that this quantity just monotonically decreases and goes to zero if we have a chaotic system. Okay, just because the state is relaxing more and more and eventually going to some steady state. This question has been studied in the classical stat mech literature. where they just considered some classical probability distributions and their evolution under the Fokker-Planck equation, which describes some diffusion or relaxation dynamics. And in that case, they found that the classical Fisher information indeed, according to this intuition, decays monotonically and goes to zero. Okay. But in contrast, if you look at the quantum Fisher information of this time-evolved state, this actually will turn out to just be a constant with time. Okay.
Right, an example that you have, this monotonic one, was this time-dependent Brownian noise, you know?
I guess, yeah, it was a Fokker-Planck equation, which I think corresponds to some Langevin equation, which is like some Brownian noise.
Yeah, time-dependent Brownian.
Yeah,
Yeah, that would be crucial.
I expect so, yeah. Yeah, Langevin equation has time-dependent randomness, that's right. Yeah, but then in the quantum system, if we consider the whole system, and remember the quantum Fisher information corresponds to optimal measurements on the whole system, that apparently gives us that our ability to estimate time doesn't decay at all with time. Okay, so in particular, if you consider a pure state, then this quantity is just proportional to the energy variance of the state, which we know is a constant for all times. And in particular, if you have an energy eigenstate, then this quantity is zero, which makes a lot of sense because the energy eigenstate doesn't evolve with time, so there's nothing you can do to figure out time from its evolution. But on the other hand, if you have some typical product state in the system and some local Hamiltonian, then the energy variance is proportional to the volume of the system. So in this case, you can do a pretty good job of estimating the time if you have access to optimal measurements on the whole system. And your ability to do this is just a constant with time. Okay. So yeah, so this is telling us that at any time t, if we're allowed optimal measurements, then rho of t and rho of t plus dt can be distinguished equally well independent of t. And this is similar in spirit, but different in detail from the statement that the von Neumann entropy of the whole system is just a constant in time under unitary evolution, which tells us that information is conserved for any time in the whole system. Here it's telling us something about how the state continues to evolve just as much at any later time as it did in the beginning. Okay. So to recover something that's more consistent with our intuition about thermalization, we can consider the reduced density matrix rho A of t of some subsystem, and the associated quantum Fisher information with that, which involves some commutator like this appearing inside the partial trace, and then again, some expression involving both the eigenvalues and the eigenstates of the reduced density matrix. And yeah, so the fact that it depends on the eigenstates as well as the eigenvalues will be pretty important. And actually, not just the eigenvalues and eigenstates of the reduced density matrix, but also on this whole global state psi of t. This can be seen as a projector of psi of t. So yeah.
The sum pi minus pj not equals to 0?
No, plus.
Because these are positive numbers.
Yeah, so I just mean that both pi and pj should not be 0. But if one of them is 0, then it contributes.
You're projecting to the, of course.
Yeah.
Supported.
Yeah. Yeah, but it's pretty important that like say pi is 0, then you still want to. So in this expression, suppose that we had like we didn't know what actually happens, and we assumed that our time evolved state was e to the minus beta h. Then that just commutes with h, so we would just get 0 for the Fisher information for all times. Okay, even for any subsystem. But yeah, okay. And then one slightly technical point, which will be important later, is that if I can always get some Schmidt decomposition of any pure state on the whole system, which will involve some Schmidt coefficients and some Schmidt vectors. And I can give an explicit expression for the time evolved Fisher information in terms of the Hamiltonian, the Schmidt coefficients, and the Schmidt vectors of both A and A bar, even if I'm interested in just the Fisher information of A. Okay.
So I think it's an experiment. So
yeah.
Okay, as you have already explained this, well, let me first make sure rho t is a density matrix of the whole system, not the reduced density matrix, right?
Yeah.
T,
Yeah, rho t is like psi t outer product.
as we have already discussed, this rho t, the unit evolution can never be given by
I know.
of minus beta h.
Yeah.
And what is the point of
of this comment?
Yeah.
I want to contrast with this. I want to contrast what actually happens with this case where I didn't have some unit, like I didn't know that my evolution was unitary.
So, but another, so a vanishing FA does not require that rho T must be written this way. Even when rho T is not written as a summa distribution, we could still have the possibility of having vanishing FAT. That is, a vanishing FAT.
Having what a
Vanishing FAT.
variation
Vanishing.
vanishing. Yeah. I want to see how, like, whether, so this is the thing that I want to compare to based on my intuition of thermalization. If the late time value goes to this, I want to find now from this actual expression where I don't assume this, but take the actual state psi of t, what do I get and how close is it to 0? So that was the only point of writing this. Yep. Great. Other questions? Yeah, so and then another thing you can notice is that because it's not just written in terms of the eigenvalues, unlike the entanglement entropy, the Fisher information of A is not going to be equal to that of A bar. In fact, it's going to be very different. Okay. Okay, so now let me just first discuss the results of this quantity for chaotic and integrable spin chain systems. Okay, so the setup that I want to consider is that I have some chaotic spin chain like this, where this particular choice of parameters has been shown from many different diagnostics to be highly chaotic. And yeah, so if we consider this model and we consider more standard observable like the entanglement entropy, then it turns out that it reproduces in a very nice way just universal features of chaotic systems. So if we had started with an initial random product state in the system and consider the evolution of the entanglement entropy of a subsystem, then it would show linear growth followed by saturation. Okay? And that is very similar, for instance, to the behavior that is seen in holographic CFTs. And the final saturation value is very close to the page value that I earlier mentioned from random pure states on the whole system. Okay. So now we want to consider in this system that we have n qubits in our chain, and we want to consider a subsystem of size NA. And sometimes I'll use dA and D to refer to the dimensions of A and the whole system. Okay. So here, the first thing we find is that if we consider a subsystem smaller than half of the system, so in this case, I've just considered a subsystem consisting of one spin, and I'm increasing the size of the whole system from 8 to 12. Okay, and I see this kind of behavior. So this is on a log scale, and I find that I see this kind of monotonic decay, followed by a saturation value, which is approximately proportional to the, the saturation value is decaying exponentially with the size of the big system. Okay. Yeah, so in particular, if I do a more detailed study of the dimension of the dependence on the dimension of the smaller system and the larger system, and I find a behavior like dA squared over D. So up to the halfway point, and especially when A is small, this is a very small final value, which confirms our intuition from thermalization that this quantity should decay monotonically and then become very small. Okay. Yeah.
Is this periodic computation?
Yeah.
And is this exact analyzation?
Yeah. And I'm considering an average over initial random product states. So I'm averaging over, say, 200 initial states. Okay.
You don't average, will the noise be compared?
It's very significant. But not as much as the integrable case, which I'll discuss later. Okay. Okay, so this is good because up to this point, especially when the system is small, we get something quite consistent with our expectation about thermalization. But if we consider a subsystem bigger than half of the system, then we see a very different story. So now here I fixed the size of the whole system, and I'm increasing the size of the subsystem and not plotting on a log scale anymore. And I find that, up to the halfway point, the final value is small, but then it suddenly increases a lot, and it starts to scale with the size of the subsystem. Okay. And if you do a more detailed study again, then you find that the saturation value is approximately proportional to the size of the subsystem for bigger than half. Okay. So, and as you can see, not only is the saturation value pretty large, but it shows this non-monotonic behavior where it initially decays and then increases. And this increase at intermediate times is very counterintuitive to me based on our intuition about thermalization, that things should be slowing down at late times in the system. Okay, so we've learned that for bigger than half of the system, our intuition from thermalization is completely wrong.
Expect some sort of a uncertainty relation between the
Yeah,
this plus before average, because averaging confuses me. But if you didn't average, you expected I would have expected that QFI for region at time t plus QFI for the complement region at time t will
is a
not-
constant or something.
I'm not
Yeah,
sure
it's
what
very
constant
funny,
is, but upper bounded and
Yeah, so you're,
lower bounded nicely.
yeah, so there are relations like that, but actually not in the obvious way that you would expect. So there is a natural way to divide the expression for the Fisher information into two terms. And it turns out, so roughly I can yeah, how is this? Yeah, let me not explain what the two terms are, okay? But so I have that I can write FA as some FA plus FA minus. Okay, and then under this decomposition, which is natural for some reason, it turns out that FA plus FA bar plus is equal to a constant, which is just equal to something like related to the energy variance on the whole system.
My intuition comes from the fact that I expect a relation like that for relative entropy to hold. And the reason for that is that relative entropy is basically an entropy term plus a modular Hamiltonian term. The entropy terms definitely will have a satisfying nice relation. Modular Hamiltonian, if it's a local modular Hamiltonian, then it will satisfy a nice relation, but in general, it won't be. So
I
that's
see.
why.
Interesting. Maybe we should discuss that more later. But yeah, but this part satisfies a nice this kind of relation, but it turns out that like FA minus is equal to FA bar minus. So it's not quite so straightforward that you could have just seen the decay of the first quantity and inferred that the other one should have the opposite
You've
decay.
also averaged, which completely.
Even without averaging. This statement is true without any averaging.
I see.
And the role of the averaging is just to make the plots more smooth, but roughly each realization has this similar behavior, and we expect that as the system size gets bigger, it should get more and more self-averaging. So the averaging should not be very important. Okay. Yeah, so this is what we find. And let me also mention the results in the integrable case. So if I turn off the longitudinal coupling, then I end up with an integrable case of the model, which is just a free fermion system. And in this case, if I make the same, the analog of the first plot that I had made, where I fix the subsystem size and then increase the size of the bigger system, then I see something very different from what I saw in that case, where I see some initial decay, but then the saturation value is not scaling with the system size at all. So it's not decaying with the size of the larger system. And roughly, it's not exactly proportional, but it's something which grows with the volume of the size of the subsystem throughout, like from size 1 to 10 or whatever system size you have. Okay, so in this case, and as we can see, the evolution is non-monotonic, even in the case of a small subsystem. Okay, so this quantity very sharply distinguishes between the integrable and chaotic cases in the even in the saturation value. And that's a little bit surprising if you know the results for the entanglement entropy in such models. Then between the integrable and chaotic cases, the late time saturation value is quite similar. But in this case, somehow this has to do with the fact that this quantity is sensitive not just to the eigenvalues of the density matrix, but also to the basis in which things are, this Schmidt basis in which things are entangled. That is much simpler in the integrable case than the chaotic case. Yep.
So can you explain why for each and the curves are splitting from a single point? So can you comment please on the time scale from where all the curves starts to split? Is there any points on that?
Yeah, it looks roughly like it. So there's some initial decay, and then that decay continues for a longer time for a larger system, and then it turns around. I don't fully understand the details of like the physics of what exactly is going on here.
I'm talking about that point from which the curves for different ends starts to like type GS. So is there any?
I don't think that. So part of the issue is that this integrable case is much less self-averaging than the chaotic case. So I think this is just the fact that, because you see that Yeah, so it's very hard to say anything because of the noise about like this branching, but it looks roughly like if I did some more averaging, then I would see that this continues to go down along the same curve, but just for a longer time.
Do you expect the curve, which is for the larger size, to remain like to separate afterwards, like the
Yeah.
curve?
But
Is this average off?
this is averaged over the same number of realizations as the previous case, so around 200 realizations, but it looks much more noisy. Because somehow in the integrable case, there is much more noise between different realizations. Okay, so this is nice because it's giving us a very sharp distinction between the chaotic and integrable cases, unlike the entanglement entropy, which has some differences between the integrable and chaotic cases. In particular, it also looks more noisy in the integrable case. Yeah, but this has a different scaling entirely. Okay. Good. So now let's try to understand this very particular scaling that we found in the chaotic case, which was different between less than half and more than half of the system. And that will also be relevant later for understanding the case of black holes or just generic systems. So in order to understand the scaling of the saturation values, as I mentioned in the calculation of the entanglement entropy to derive the page curve, a nice model for the late time state of the system is just a purely random pure state drawn from the uniform distribution on the whole combined system. And that gives a very just a very close numerical approximation to the value that you get in the spin chain at late times from these initial product states. Okay, so ideally we would use that model, but it turns out that for our quantity, which is more complicated than the entanglement entropy and depends on the eigenvectors and so on, it's very hard to do that calculation in practice. But we'll use a model which is motivated by random pure states and is closely related, but a bit simpler to do calculations with. Okay, so our model is that we explicitly write down a Schmidt decomposition for our state, where motivated by the fact that the entanglement entropy is just log dA at late times, we take all of the Schmidt coefficients to be equal to each other and equal to 1 over square root of dA. Okay. And then we make, I'm assuming that A here is the smaller subsystem. So we can choose any basis now that we've made all the Schmidt coefficients equal. We can choose any basis for the Schmidt eigenvectors in A. And then in A bar, we have to pick some dA eigenvectors, which are smaller than the total dimension of A bar. So we can just make some fixed choice and then completely scramble it by acting with some random unitary on A bar. Okay, so this is not a very accurate approximation to a high random state, because in that case, the eigenvalues are not for each realization exactly equal to this. There is some non-trivial distribution which shows some level repulsion. But even if you take into account that level repulsion, the answer doesn't change too much. You just get some exponentially suppressed corrections from that. Another possibility is that there could be some three-way correlations among these things in the actual high random state, but we're going to ignore such possibilities and just take the simplest model to do calculations with. And it'll turn out that the answer that we get from this is a pretty good approximation to the actual scaling. Okay. And note in particular that in this model, I haven't put in anything about the fact that the late time state has come from evolution by H, which would be really important if I was considering initial states which were strongly constrained by energy conservation, right? Like if I had considered an actual energy eigenstate of the system, then this would be a terrible approximation for the actual value of the Fisher information. But because I'm considering initial states which are drawn from this random product state ensemble, which has a very large energy variance, one might expect that if I completely ignore the effects of energy conservation by making this approximation, I still get a good approximation to the value of the Fisher information. And we'll see that that is what happens. Okay.
Sorry, your initial state has support on K energy eigenstates, and then you just replace that dA with K. You should still get some sort of a reasonable model, right?
I don't think. No, I don't think that this dA, like number of Schmidt eigenvalues, should have anything to do with the number of eigenstates, right? Because that is the decomposition in the energy eigenbasis of the state. This is like the representation at some local basis.
Sorry.
Yeah.
D of the whole thing is going to be K.
Yeah. Okay, yeah, maybe you can do some kind of microcanonical version of this.
Right.
Yeah,
The
one
DA
could try to do
squared
that.
has
We've
to
not
be
tried to
much
do.
smaller than that K.
Yeah, yeah. Yeah, maybe, yeah, it would be interesting to see what answer we get from a microcanonical version of this calculation.
People have done these kind of calculations by doing quantum information. Yeah.
Or Rennie entropies and
For
entanglement.
Rennie's,
Yeah.
yeah.
Yeah, this, right, so it would be interesting to see what you get for this quantity in that case. Right, and there are many interesting effects of energy conservation on the Rennies, so there must be some corresponding things here, yeah. Okay, taking this model, the reason that things simplify is that I'd mentioned that there's some explicit expression for the quantum Fisher information in terms of these Schmidt vectors. And once I plug into that expression, I just need the second moment of this random unitary, as opposed to if I try to do the replica trick for the original quantity using high random states on the whole system, I would have to do a very complicated replica trick and get all possible moments of some random unitary. Okay. So when I do that calculation, I end up with an answer which has this kind of form. So if I divide the whole Hamiltonian into the part in A and the part in A bar and the interaction, then I get an expression which depends on the dimension of A, the dimension of the whole system, and some moments of the various Hamiltonians. And then I can see what the scaling of these things is, assuming that the Hamiltonian is made up of some local traceless terms, like in my example. And I find that for less than half of the system, I get dA squared over d times the area of the boundary of the region. And then for bigger than half, I get a very different behavior, which is just proportional to size of A. Okay, so now with this, I can plug in, I can compare three different things. So in this plot, these circles are what I get for different system sizes. If I plot the saturation value at late times, so I can average over a few different late times and get these circles. And I'm plotting as a function of the fraction of the subsystem to the whole size of the system, the value of the Fisher information divided by the size of the system. And so this is the actual data from the numerics in the spin chain. Then the stars are if I plug into this formula plus its higher order corrections for the same system sizes and the same Hamiltonian, then I get these values, which are of course different in their numerical values, but pretty similar in the overall scaling and even not too far in the numerical values from these ones. Okay, and then I can take the n going to infinity limit of the toy model, which just gives me these expressions, which show this sharp transition at the halfway point, where it's just effectively zero and then becomes extensive in the size of the subsystem.
What is the area theorem? I'm kind of confused.
Oh, in the area term is just some, like this has trace of h inch squared. This is like if I have, the spin chain had a zi plus one term, which didn't belong to either A or A bar.
So that's how it works out.
So this is just like measuring the size of that term, which is proportional to the number of, if I had some higher dimensional thing, it would be proportional to the area.
So locality of the Hamiltonian.
Right. So, yeah, so that's the answer. And in particular, we're able to see this very sharp transition at the halfway point where this quantity suddenly becomes extensive and then continues to grow. Okay. So yeah, so now we can discuss the consequences of this for the evaporating black hole setup. So yeah, so as I had mentioned before, this is the question that we're given the radiation at some time t plus delta t. We want to figure out what delta t is. We assume that we're considering timescales which are much faster than the timescale on which degrees of freedom from B are being transferred to R. So we'll just treat the two subsystems A and A bar as either B or R in the setup. Okay, and basically what we've learned from the result that I showed is that our time estimate is very unreliable before the page time when dr is less than dB, even if we use optimal measurements. But the variance suddenly improves after the page time and then continues to improve until the end of the evaporation process. Okay, so this might seem familiar to people who have thought about sort of black hole information problem or related questions. And it might remind you of something called the Hayden and Fresco experiment. Okay, so we discussed the behavior of the entanglement entropy during the evaporation process. And in particular, we discussed how the entanglement entropy of the radiation stops looking the same as the thermal value after the page time. So in some sense, the fact that the entropy is smaller than it would be in the thermal state suggests that there is some kind of information in the radiation after this time. But that is a little bit vague. But Hayden and Preskill tried to make this sort of vague intuition much more precise by considering a precise operational task in this evaporation problem, where they imagine throwing a diary into a black hole at some early time before it starts evaporating, and then assuming that the combined evolution of the diary and the black hole is some unitary chaotic evolution. And then at a later time, the black hole has reduced in size and emitted some radiation. And we have access to the state of the radiation. And we can ask how well we can recover the original state rho d by processing the state rho r. Okay. And they found that this recovery is very poor before the page time, but it's almost perfect just immediately after the page time. Okay. And this sharp transition is quite similar in spirit to what we found. But we can try to do a more precise comparison between these two things and see if they're exactly the same. Okay. So in the Hayden-Preskill protocol, so I'm just going to rephrase that as a task of quantum error correction, where we first imagine that we are encoding one qubit in the diary. So we're trying to encode one logical qubit into n qubits in the following way, where we have some fixed initial state psi 0 and n-1 qubits. We add another 1 qubit state to it, and then we evolve them together under some highly scrambling unitary, which we can just take to be hard random for our purposes. Okay, and then we trace out the subsystem B. So overall, we end up with some quantum channel, which takes us from D to R. Okay, and then the question about whether or not you can recover information from this channel can be phrased as follows. You can ask whether any two initial states, psi d and phi d of the diary, remain equally distinguishable before and after acting with this channel. Okay, and if yes, then the information recovery is perfect. And if the fidelity decreases, then it's less perfect. If the distinguishability decreases, then it's less perfect. And if there's no distinguishability afterwards, then you cannot recover information at all. Okay, so one quantity that you can use to measure the distinguishability of the states is the fidelity. And the fidelity is equal to 1 if the states are perfectly indistinguishable, and it's equal to 0 if the states are perfectly distinguishable. And so it turns out that if you consider the fidelity of the state that you get after acting with this channel, then it's just equal to 1 if dr is less than dB, no matter what the initial fidelity was. Okay, so that means that the states have become perfectly indistinguishable on the radiation. If the radiation is smaller than the black hole. But as soon as you cross the halfway point and dB becomes smaller than dr, you find that the fidelity of the two states is equal to the original fidelity. So then you go from not being able to recover at all to perfect recovery at the halfway point. Okay, so the task that we want to consider here is somewhat like trying to distinguish, we just Taylor expand because we discussed this local parameter estimation task. We're trying to distinguish psi of t from the Taylor expansion of psi of t plus dt. And effectively, this is like trying to distinguish the state psi of t from h acting on psi of t. Okay? And this was made a bit more precise in this paper. So roughly, it's like we're trying to encode some 0 qubit into this state, and then the 1 qubit into something like this, where, of course, we should also orthonormalize 1 with respect to 0. Okay. And so our task is, and then we imagine doing some partial trace, some degrees of freedom corresponding to B. And we again get some channel where we send the 0 and 1 states on the diary to some corresponding states on the radiation. And we want to ask how well we can distinguish them. But as you can see, the configuration of this task is not the same as the previous one, because here we're not using the whole power of the random unitary to scramble the information. We're just mapping them first to the same state using U and then changing it a little bit by acting with H. Okay, so this is not as good of an error correcting code as the previous case, intuitively. We can check that more precisely. So we can ask about the, so we can calculate in the same sort of model for the late time state that I had mentioned before, which is somewhat like a hard random state. We can calculate the Holivo fidelity, which is the easiest thing to calculate in the setup of the states 0 and 1 after acting with this channel. And we find that again, they're perfectly indistinguishable if dr is less than dB. But there's a sudden improvement at the halfway point, where the fidelity reduces from 1 to 1/2 if dB is less than dr. And then it continues to decrease gradually from 1/2 to 0 over the course of the rest of the evaporation process. And then it becomes perfect only at the end. Okay, so it's not quite as like it's not from absolutely indistinguishable to perfectly distinguishable, but there is a sudden improvement at the halfway point. Okay. Okay. So yeah. So now let me try to give some further interpretation of what we're seeing in terms of the structure of the time evolved state. So actually, I think I'm technically close to the end of time. Is it okay to go like, yeah, maybe 10? Yeah. Yeah. We'll see what happens. Okay. So the fact that as I already mentioned, the fact that we get a small late time value in the case of less than half of the system is fairly intuitive from our previous understanding of the fact that this reduced density matrix at late times really approaches something like the maximally mixed state for the particular initial states we've chosen at late enough times. Okay, so in particular, these authors showed under certain models and assumptions that this distance between the time evolved state and the maximally mixed state is becoming of order dA squared over d.
This is
Yep.
what I meant when I say instead of the quantum information. These papers.
Yeah. Right. Exactly, but it's, as I'll explain, it's closely related. Makes the result very intuitive, but it's a bit different because, okay, firstly, this is the average of this quantity over all times t. And then these authors also considered sort of fluctuations from this time average at any particular time. And they found that that also becomes pretty small at late times. Okay. And what we found here is something a little bit different because it's related to the speed of the fluctuations, which is like this time derivative of the distance between t and t plus dt. Which in principle could have been, could have had a different scaling from this, but in practice, we're finding that it has exactly the same scaling. Okay, so we're finding that not only are fluctuations very rare and very small, but they're also very slow.
Sorry,
Yeah.
the technique that was used to actually derive that inverse inequality is concentration of measure.
Yeah.
Which in principle, I bet that's what Kotler and friends did.
Kotler and friends did something, they didn't quite do anything at the same level of rigor, and they didn't derive as d squared over d scaling, but they were looking at a spin chain. Well, they did a few different things.
I mean, you could use concentration measure to get a sense of their fluctuations. That's what I'm saying. Because those guys, they
Yeah.
just cooked up one inequality because they thought of that one. But they could have written more if they wanted to.
Yeah.
We'll discuss it.
Right. But in any case, the speed of fluctuations is something which in principle can have a different scaling from the actual absolute size of the fluctuations. So this is, but then it's fairly intuitive that the speed is also very slow, and we've recovered that intuition. Okay. Good. So the story for A is pretty intuitive. What we don't often discuss is the structure of the reduced density matrix of the larger system A bar, other than its eigenvalues, which are just captured by the entanglement entropy. And yeah, we're finding that that state is changing very rapidly at late times. Okay, and if you think more closely about it, then that perhaps should also be intuitive, because at late times, we know that the eigenvalues of that reduced density matrix on A bar just approach 1 over dA. But there are dA eigenvectors of that reduced density matrix in the whole dA bar dimensional space. And they're not really constrained by anything. And what we're learning is that they sort of freely and very rapidly explore the whole Hilbert space that's available to them. So that is somehow what is being captured by this large value of this quantity at late times. Okay. Yeah, so right. So we have some picture like this where the small subspace of eigenstates of A bar is swimming around in a much larger Hilbert space. And we found that there's some still some universality in the speed at which that happens, even though there isn't a universality in the actual structure of these things. Okay. Yeah, so then we can also understand the fact that there was some increase in the value of this quantity at intermediate times for the larger subsystem by making a simple model where, say, we are mostly interested in the evolution of these Schmidt eigenvectors. So we'll ignore the time evolution that's associated with the eigenvalues of the Schmidt coefficients. So we can just assume that those have already equilibrated to 1 over dA to the 1/2. And then the only thing that's changing is the structure of the eigenvectors. And just to make some simple model, we can say that this is some time-dependent random Brownian evolution. Okay, we're making some simple time-dependent model for this where we can do actual calculations. And the point is that this is something which gradually approaches a random unitary at late enough times. Okay, and under this model, we essentially find that for the smaller subsystem, the quantum Fisher information monotonically decreases, and for the larger subsystem, it monotonically increases. So the increasing part at late times can be seen as the effect of this kind of process where at later times, we have access to more and more of the large Hilbert space of dA bar for the eigenstates of rho A bar to explore. Okay. Yeah, and then in the integrable case, again, we can understand what the reason for the very different behavior from the fact that there's some very simple model for the Schmidt decomposition of the state at late times, where we can assume that somehow in that case, even though the entanglement entropy grows, it grows because of some, we can imagine that at the initial time, for some reason, there was some initial pairs of nearby entangled particles that were created, and then they just free stream away from each other and carry the entanglement to longer distances. And in particular, this means that unlike the very random assumption that I made for the Schmidt eigenbasis in the chaotic case, the Schmidt eigenbasis here is very simple in both A and A bar. And by putting that into the expression for the quantum Fisher information, you can see why the result in that case doesn't decay with the size of the larger subsystem. Okay. Okay. So let me quickly mention in the remaining time a different kind of coarse graining that we can do. So where, yeah, instead of considering the optimal measurement basis, which gives us the quantum Fisher information, we'll just consider the classical Fisher information in the computational basis. Okay, so that is another way to consider a simple measurement, but now not restricted locally. Okay, so yeah, so just to have some point of comparison again, for the thermal state e to the minus beta h, we found that the quantum Fisher information was equal to 0 for any subsystem. And so there was an infinite uncertainty in estimating time for this state. We found that if you consider the state obtained from some unitary evolution, then I'm going to phrase everything in this black hole and radiation language, although the statements are also more general. So the quantum Fisher information of the reduced density matrix of the radiation was exponentially small in the size of the system before the Page time, which is very close to this value of 0. But then, and was essentially indistinguishable from the value in the thermal state. But then after the Page time, the value became of order n, so it was very sharply distinguishable from this value of 0 in the thermal state. Okay. Yeah, but then this is the quantum Fisher, this is associated with optimal measurements on the radiation. But now we can ask, what if we consider simple measurements on the radiation? In this case, so we fix the measurement basis to be the computational basis and study the associated classical Fisher information. Okay, and intuitively we expect that if we consider simple measurements, then even if we have access to the state of the radiation, then there's some kind of information loss and we recover something like Hawking's result. And this intuition was provided, for instance, in works by Engelhardt and Wall. And so based on this expectation, I would guess that if I restrict it to simple measurements, then even if I consider the larger subsystem, the value of the corresponding classical Fisher information for simple measurements is close to 0. Okay, so we can first consider the case of just the full system where I restrict to simple measurements. And in this case, so this is like in the black hole case, considering the radiation at the end of the evaporation process. And here I find that the intuition based on information loss from simple measurements is not correct. So I find this evolution of this computational basis Fisher information where it does decay a little bit from its initial value, but the final value is shown for different system sizes. And as you can see, it's growing with the system size. Okay, so it's actually still volume law and very different from the value of 0 in the thermal state. Okay, and the dashed lines are what I get in the random state for this quantity, which is again very large. Okay, so the simple measurements are actually not losing information if you have access to the whole system, which is somewhat counterintuitive. But then you can ask what happens if I restrict the size of the subsystem. So if I consider a subsystem A, which is bigger than half of the system, but not quite the full system, then I find that the computational basis Fisher information scales as the size of the system divided by the dimension of A bar. Okay, so so it actually, like in the case where dA bar is just equal to 1 because there is no complementary subsystem, this is large, but it very quickly starts to decay. Okay, so for instance, here I've shown what happens to this quantity if I fix the system size to be 7, which in each of these cases from 8 to 11 is bigger than half of the system. Then this quantity is still decaying with the size of the whole system. Okay, and this is in contrast to if I consider the quantum Fisher information, which is associated with optimal measurements, which if you look at, so it looks like it's decaying a little bit with the size of the bigger system, but if you really look at this axis, these numerical values are very close to each other. So this quantity is not scaling with the size of the whole system, whereas this one, it does decay exponentially with the size of the complementary system. Okay, so yeah, so in the black hole case, this means that there's some exponential decay of this quantity with the number of qubits in the black hole. And in particular, the value of this quantity is able to distinguish between the thermal state and the actual state only very close to the end of the evaporation process, where the number of qubits in the black hole is logarithmic in the size of the whole system. Okay. Yeah, and in principle, this can also give us an operational way to distinguish the state of the radiation from the thermal state at late times, because we can give some operational way to measure the Fisher information as follows. We make some n measurements in the computational basis. For each of them, we come up with some maximum likelihood estimate for t based on our measurement outcomes. And then we repeat this k times, so we get some series of k estimates for the time. Okay, and then we can calculate the sample variance of these outcomes T1 through Tk. And then by the law of large numbers, for large k, this should approach this theoretical variance. Okay, and then we further expect that the theoretical variance for large n approaches its value of 1 over n times s. Okay, and while n and k need to be large, there's no reason why they need the number of n and k has to scale with the system size. Okay, so yeah, so that gives us some operational way of distinguishing the state of the radiation from the actual thermal state at very late times. And it turns out that you can also, like another quantity which distinguishes the state of the radiation from after the page time from the actual thermal state is the second Renyi entropy. And the second Renyi entropy in principle also gives us an operational way of distinguishing the two things using something called the swap test, which is a simple thing to do. It's a simple operation, but it has a very large sample complexity unless you're in the same time regime that I mentioned, where NB is of order log n. Okay, so somehow from these two very different perspectives, we seem to be learning the same thing, which is that it's hard to distinguish the black hole, the thermal state of the radiation from the thermal state, except in this very late time regime for some reason. Okay, yeah, and since we're already way over time, I guess another thing you can do is look at the classical trace distance between the probability distribution on the computational basis and the uniform distribution, which you would get from the thermal state. And that recovers similar intuitions to what you get from these other two ways of trying to distinguish them. So I can go into that more later if people are interested. And here's a summary. And yeah, maybe a final question is just whether if we could do this calculation in semi-classical gravity. I've told you what the unitary answer is and what the analog of Page's calculation is, but it would be interesting to see if we also see some kind of information loss for more than half of the system from the perspective of this quantity, if we could do some semi-classical calculation. And then if that would be resolved in a similar way to the way that Hawking's information loss paradox was resolved. So that's it.
Other questions for sure?
Two questions.
Okay.
I want to make sure that I understand some basic things correctly. So it looks like the criterion of summarization based on the Fisher information setting has to vanish. in non-times.
Yeah,
Yeah, well, but you have shown that, well, if we consider small system,
Mhm.
still there is a small amount of communication information.
Mhm.
That is proportional to an A. Then how could these two results be consistent with each other?
oh, so it was proportional to NA in the case of the integrable system, but in the case of the chaotic system, it was proportional to DA squared over D.
Oh, so it eventually vanishes.
It's very small at daytime. Yeah, the initial value is proportional to NA just because it's equal to the energy variance. So we have some product state. The initial value is equal to the energy variance of the initial state, which is of order NA. But that decays to a small value. Yeah. Mhm.
Then my second question is, so in other cases, we just use thermal entropy to characterize whether or not it's summarized based on the volume law versus area law. So now you are proposing a alternative scheme using this communication.
Yeah, it's a different question from the
But
one.
it's not, these two schemes actually should give us consistent results, right?
Mhm.
But in the countries whether or not there are any numerical or analytical arguments that these two criteria actually are consistent with each other. Say when the confusion information really vanishes eventually, times, then some entropy must satisfy certainly.
Yeah, I can imagine getting some criterion in that direction because the quantum Fisher information is taking into account both the eigenvalues and in some sense the eigenvectors. I can't imagine something in the opposite direction because the entanglement entropy only knows about the eigenvalues. But I'm not sure if, yeah, maybe there's something like that, but I don't know yet if it's possible to say that.
Yeah,
So then the
it
countries
could go the other way as well, but some of us contrived setups, I think.
Okay.
Unless you know when the communication information vanishes, whereas the information must satisfy this problem.
But you could imagine that it vanishes in some other way without, yeah, I'm not exactly sure. Like you might need some additional inputs because in principle, these two things are probing different questions and
Yeah, but,
yeah.
but if both of them are correct, they should give us consistent results.
Yeah.
Any other questions?
Like a trivial question, because it seems, suppose I have a black hole initially it's in the pure state. The state starts to evaporate. But at the very beginning, suppose I have the radiation, I measure how much energy I in the radiation. Cannot I determine the time from there? Because at the beginning you are supposed not to be able to determine time.
Right, but I think that this is because I'm considering estimating time on a smaller scale where I'm not trying to count the number of degrees of freedom in the black hole and radiation. I'm imagining that I have I'm considering timescales which are faster than the scale on which things are transferred from the black hole to the radiation. I'm considering for some fixed size of the black hole and radiation. Is the state of the radiation still changing between some time t and t plus dt, where I can assume that the number of qubits in the radiation hasn't really changed. So that cannot be measured just by counting the number of things in the radiation.
I have a question about the mixed field Ising model variance. So I was wondering if similar calculations could be done either designing or analytics for SYK, like the one Fisher.
Possibly. We haven't tried doing it. It seems like it would. We can certainly do it numerically in SYK, up to some size, but
Maybe the large.
maybe, yeah. But it seems like it would be quite complicated just because of needing to know. Like we might have to do. In principle, you can write the Fisher information as some replica trick, but that is a very complicated replica trick. So that might require calculating very high moments of various things.
I suspect Brownian SYK is easy,
Brownian SYK would definitely be easier.
and then you actually expect monotonicity.
Monotonicity means.
Monotonic decay of F or smaller than half.
Which also roughly translates to a monotonic increase for more than half.
I have a question as well. Can you say again, what was your definition of simple operators, in this context? So there's
Yeah, I
multiple
just,
operators?
right, by simple, I just mean something which doesn't have a very high computational complexity. I guess, one thing that is definitely simple is the computational basis. So I haven't used a very strong notion of simple or complex in this.
There is a notion, there is, an information theoretic way of making sense of this, which is, an operator, you would say an observable is simple if the number of outcomes is small.
mm,
So
that is not true of this one, because,
yeah, that is something that people could get some quantitative handle on. Because people approve statements for those operators, optimization of those operators.
yeah, I'm considering a measurement, which I think is simple to implement because all I have to do is measure the Pauli operator independently at each site. But it's true that the number of measurement outcomes is 2 to the n.
Yeah.
But I don't think that makes it complicated to do.
Yeah, so that's
Yeah.
not the only way of defining.
Yeah,
simple
yeah, yeah,
operator, But I
yeah.
think these simple,
Yeah.
these operators these guys talk about are definitely simple.
Mhm.
Not all operators simple operators.
Right. But I think so, if I consider the optimal basis, then that would be some highly entangled basis to measure in. And in contrast to that, the measurement basis that I consider in this last part of the talk is just product states of zeros and ones, which is a very simple basis to measure in.
The reason, just one last thing, the reason that people talk about less number of outcomes,
Yeah.
because it's coarse grained.
Yeah. So actually, by such things, I think if you restricted the number of outcomes, like for instance, I just chose to I think if I considered a version of this where I had a smaller number of outcomes, then I would find that there is information loss even on the whole system.
Absolutely.
Yeah.
Absolutely.
Yeah.
Any last questions for Shreya? Not, let's thank again.
Thank you.